We are Triton Unmanned Aerial Systems from the University of California, San Diego, presenting our aircraft, the Stickbug.
This year's competition displays a multitude of requirements that must be fulfilled to have a successful mission. We are required to fly an autonomous waypoint mission and drop 5 water bottles on 5 discrete targets, all within the 30-minute flight time. Based on the timeline required, our selection of a VTOL fixed-wing aircraft configuration allows for quick and easy autonomous takeoff and landing up to the 75-foot altitude. And its 8.5 wingspan increases the aerodynamic efficiency in forward flight. We have also determined the acceptable flight velocity to be 20 to 25 meters per second, which allows for minimal error during the waypoint mission and a small turning radius of 30 feet. We are also required to have a max takeoff weight of 55 pounds, and based on this, our aircraft is solely created out of lightweight composites, including carbon fiber, fiberglass, and wood.
Our system is divided into two main parts, the aircraft and the ground control station. The aircraft contains two main computers, the Cube Orange flight controller and the NVIDIA Jetson Orin Nano. The flight controller runs Arduplane and handles all aspects of the autopilot itself. The Jetson, dubbed the onboard computer, handles all mission-related logic and is programmed entirely by our software team. The onboard computer is connected to the flight controller via a serial connection and sends Mavlin commands to control the autopilot. It also handles interfacing with our Lucid Triton camera and communicating with our drop payloads. On the ground, we have our in-house ground control station software, dubbed the Hub. This is a standard web application with a React front-end and a Go backend that runs on an Intel NUC. The backend handles all mission-related communications between the ground control operator and the aircraft, while the front end provides a nice user interface to monitor these communications. During a mission, one operator is required to handle these tasks, with an additional operator for the fourth optional task. Number 1, input mission parameters to the plane. Number 2, monitor connectivity with all the different nodes of the system. Number 3, monitor autonomous mission progress and flight telemetry. And 4, which is optional, provide manual overrides for matching detected targets with airdrop bottles. In order to communicate between the ground and the plane, we have two different communication channels. The first is a radio link between the ground control station and the Cube Orange autopilot, facilitated by two RFD 900 radios. This radio link is used to send Mavlin packets directly from the autopilot to the ground controller. This is what is used by the ground control station to display the plane's telemetry location. In addition, the ground control station also sends this telemetry information to our antenna tracker, which points a directional Wi-Fi antenna at the plane so we can extend our local area network to the onboard computer. The antenna on the ground is a Ubiquiti nanostation, and the antenna on the plane is a Ubiquiti Rocket AC. Via this Wi-Fi link, we send messages to the onboard computer. Some of these messages include uploading mission specifications, validating computer vision results, and certain manual overrides. In addition to all of this, we also have our safety pilot, who can take control of the plane at any moment using his RC controller. Overall, to operate our system, it takes two people, with an optional third. The two mandatory operators are the safety pilot and the ground control station operator, and the third optional operator is a second ground control station operator, whose job it is to validate our computer vision and machine learning algorithms which match identified targets to airdrop bottles.
Triton UAS has elected to use the Triton 200S camera made by Lucid Vision Labs. The camera has a 20 megapixel sensor, which we are pairing with a 50mm lens. This sensor and lens combination gives us excellent resolution of competition ground targets. At an altitude of 200 feet in the air, the competition targets appear with a width of 25 pixels. At 75 feet, the same targets appear as 50 pixels. This resolution is more than plenty for our computer vision models to accurately detect the targets. The team has fine-tuned the camera's auto-exposure algorithm to capture images that are clear in a variety of lighting conditions. In addition, we have built a custom camera gimbal that will stabilize the camera during the mission. Our 2-axis camera gimbal uses brushless DC motors with custom-written motor controllers, combined with an extremely light and stiff forged carbon fiber structure. Our gimbal was designed with precision and stability in mind, allowing it to maintain a fixed stare at the ground under any aircraft altitude changes. To perform identifications of ground targets, the team has developed a multi-stage pipeline for our image processing. First, the high-resolution aerial images go through the saliency stage, where the ground targets are detected. This stage produces several bounding boxes, which indicate exactly where the targets are within the image. Saliency is implemented using a faster RCNN model, which is trained on our own artificially generated dataset. This model is also responsible for classifying targets between standard and emergent. This next stage of our pipeline is our matching stage. We use a contrastive model to compare the crop targets from saliency to the targets specified by the competition. The model gives us a similarity measurement between the targets from saliency and the expected targets. Then, we can determine which targets match up closest to the expected targets from competition. Finally, the matched targets go through the localization stage, where they are assigned a latitude and longitude. The localization algorithm uses the position of the plane to convert the pixel coordinates of the target into real-world latitude-longitude coordinates. We have tested our imaging pipeline from the tops of buildings and during flights from 75 to 100 feet. The saliency model performs well, with accurately detecting 92% of standard targets. When it comes to emergent targets, the saliency model can accurately detect 58% of emergent targets. The localization stage of the pipeline is accurate to less than 10 feet away from the expected position.
Our airdrop system was designed from the ground up to ensure safe and accurate delivery of payloads. The payloads are loaded underneath the wings and use a parachute to reduce the rate of descent to a safe level. The housing of the payload, which contains the water bottle as well as electronics for guidance and navigation, is made of a flexible 3D printed TPU to better absorb energy on ground impact. The release mechanism we decided to use involves 2 loops of bungee cord that secure the payload to the underside of the wing. When the payload initiates the drop, 2 servos passively holding the ends of the bungee cord let go and the payload falls. To inform the optimal parachute system, we extensively tested the parachute deployment and release mechanism before integrating the airdrop system onto the plane. This involved the investigation of multiple different chute designs, stringing methods, and folding techniques. As the mission progresses, targets are identified and the onboard computer determines which bottle should be queued for drop. Using the onboard GPS module, the active payload checks if it is within a reasonable distance of the target, and then releases itself from the aircraft. The remaining horizontal distance is covered by the payload as it adjusts its glide path using 2 internal servos. In order to send messages to the payloads, the team designed a custom networking protocol that is built on top of UDP broadcast packets. The onboard computer hosts a Wi-Fi hotspot to which the payload devices can connect. The protocol allows the payloads to declare 2 possible modes of drop, direct and indirect. Indirect drop is the preferred method as it is designed for the guided nature of our payloads and involves the onboard computer uploading drop coordinates to each payload and then signaling when it is a specific payload's turn to drop. Once a payload has been signaled, then it checks whether it's close enough to the target before dropping. The onboard computer can also revoke drop privileges for any reason, and this is typically used if the plane must dynamically avoid another aircraft. However, the team also developed a protocol for direct drop as a fallback option, and it involves the onboard computer itself sending a drop now signal to a payload when it is time to drop.
So as shown in our communication systems diagram, we have 3 communication links between the ground control station and the aircraft: a manual radio control link, an autopilot telemetry link, and a Wi-Fi data downlink. The RC control system provides the ability for the safety pilot to override the autopilot in case of autopilot malfunction, and therefore this link is critical to the overall safety of the mission flight. To provide this link, we use the 2.4 GHz band FR X8R. In addition, it employs frequency hopping technology to prevent jamming and minimize the impact of potential radio interference. The autopilot telemetry link provides real-time feedback of the autopilot state, as well as the ability for the autopilot operator to send commands and waypoints to the aircraft. We chose to use the RFD 900 modem, which operates in a 900 MHz band due to its demonstrated performance at 60 km without requiring high-gain directional antennas. The Wi-Fi data downlink enables the transfer of images from the onboard computer to the ground control station and provides an interface for the payload systems. Since this Wi-Fi link must maintain relatively high bandwidth at long ranges, we chose to use the Ubiquiti Rocket AC due to its ability to sustain a connection up to several miles. Due to the high directivity of the antenna, it's vital that the plane is kept within the antenna's area of peak gain. To accomplish this, we use an antenna tracking device which is placed next to our ground control station, which uses both the telemetry data of the plane and its own location data to determine the proper pitch and yaw to maintain a strong connection. Our distance versus bandwidth graph summarizes the results of this testing. However, even with this setup, the communication system will not be able to transmit full-sized images taken from the plane to the ground at a reasonable speed. Thus, the onboard computer is used to crop the images to only contain relevant data, which is then sent to the ground. In turn, this greatly reduces the bandwidth demands of the computer vision system.
For aircraft design and testing, we established 12 technical subteams entering the 2023 and 2024 competition to cover all technical aspects required for the overall aircraft operations. Looking into manufacturing choices that led to a reliable and reusable competition aircraft, we established a design for maximized strength to weight capabilities through the utilization of 1. Carbon fiber skins for our wings, fiberglass skins for the fuselage, which allowed for reliable communication with ground operations, balsa wood and basswood as opposed to plywood due to their reduced weight to strength ratios along with carbon fiber tubes for internal wing structures, which encompassed all spar, shear web, and rib segments. And lastly, plywood was chosen for internal fuselage structures, including the bulkheads, battery platform horizontal motor mounts, in order to withstand the weights of in-flight hardware and provide adequate protection if any unforeseen circumstances occur where the aircraft receives an excess of impact. All composite manufacturing was executed via a wet layup molding process where we manufactured mold negatives to complete layups for the carbon fiber wings along with the fiberglass fuselage. The mold negatives were printed via 3D printing in order to achieve complex geometries on both the fuselage and the wings, such as twist, taper, and airfoil shifts, along with the decreasing in overhead costs that would be then associated with the machining molds. The tail was not completed via the molding process, but rather was a direct carbon fiber layup onto a foam core airfoil, which allowed for us to achieve a reliable rotor-vator inverted V-tail design. Propulsion consists of 5 motors: 4 Sunny Sky X62 15S KV170 motors located on the 2 tail booms which creates a stable square orientation for VTOL, and 1 Scorpion S2 5525 170 kV motor placed at the rear of the fuselage supplying forward thrust. Each VTOL motor is capable of providing over 18 pounds of thrust, spinning a 22 by 6.5 inch prop, and the forward propulsion motor paired with the 20 by 10 inch propeller is capable of approximately 20 pounds of thrust. Controls include a singular aileron on each of the wings and 1 control surface on either angled face of the inverted V-tail. The V-tail design was chosen to avoid the effects of propeller downwash on the tail. Operations of the rotor-vator allows for both yaw and pitch control through the same control surface. For all 4 control surfaces, we utilize the KST X10 V8 servos due to their qualifications of torque output, along with the low profile, making it simple to embed into the wing and tail while maintaining a streamlined profile.
For our autopilot, we use the Cube Orange flight controller running RDUPlane version 4.5.1, which provides robust control of the aircraft for both manual flight and flying waypoint missions. We chose the Cube Orange for its excellent sensor package, widespread adoption, and extensive documentation. Our onboard computer is responsible for dynamically path planning and integrating each subsystem on the aircraft, from the camera gimbal to the airdrop. The onboard computer sends this information to the Cube Autopilot and lets it carry out the flight control computation. We have tested our autopilot performance on a variety of autonomous missions, varying from simple square circuits to more complex waypoint sequences that follow the edge of our flight zone. Overall, we have flown 4 autonomous flights, and in these flights we spend an average of 1 minute in manual mode during takeoff and landing. We've attempted 55 waypoints and have successfully hit 51, and on average we miss a waypoint by 7 feet.
We use a modified version of the RRT star algorithm to generate the initial flight plan for the aircraft to ensure that the plane stays within the competition boundaries. This initial path routes the plane such that it travels through each waypoint in series and then covers the entire drop zone so we can take aerial images of the targets for identification. Once this is completed, we use the same algorithm to travel the calculated drop points for each bottle, interspersed with the same waypoint path we generated at the start of the mission. In order to dynamically avoid other aircraft, we use a zero-shot segmentation model, fast SAM. If we detect an opposing UAS on our projected flight path, then the action we take depends upon the current phase of the mission. If we are flying the waypoint or airdrop search portions of the mission, we attempt to continue on our projected course while simply adjusting our altitude. If we are currently performing the airdrop task, however, we abort our current approach and return to a predetermined loiter position to wait for a short period of time before trying again. We have verified the RRT star algorithm using several mock missions while observing the length of the path and how accurately it reaches the waypoints. We uploaded these generated paths first to our virtual plane to verify that we did not go out of bounds and that we accurately hit our waypoint goals. Once we deemed this path generation to be correct, we attempted missions on the physical aircraft and observed the flight results and logs. In all of our missions, we have successfully met the 25-foot threshold for nearly all waypoints, and the main variance in performance seems to be caused by wind conditions. Ideally, the team would have liked to use a robust implementation of our modified RRT star algorithm to do path planning in real time based on detected stimuli from our dynamic avoidance CV algorithm. However, we determined early on that this would be too complicated for a number of reasons. First, we were already doing a full rewrite of our onboard computer software in C++, and adding in the extra complexity of a fully dynamic pathing system seemed overly ambitious for the time and resources we had available. Second, assuming that we had a robust plane detection algorithm, we determined that the most potential collisions could simply be avoided by adjusting the aircraft's altitude. With these reasons, we spent the bulk of our time on obstacle avoidance, focusing on getting a robust plane detection algorithm, and implementing our static path planning algorithm, as described in earlier portions of the video.
One of the biggest decisions that needed to be made early on in the aircraft design process was the aircraft configuration. We previously had built standard fixed-wing aircrafts as our competition aircraft, which has proven to travel at higher velocities and at higher efficiencies in forward flight, which is beneficial for less battery strain and faster competition task completion. However, our previous aircraft have struggled during the testing phase, as bad runway terrain and weather have hindered the quick repeatability that is required to test all of our systems in the proper time frame. Therefore, our main configuration was decided to be the VTOL fixed-wing configuration. VTOL allows us to take off and land without dependence on good weather and a stable runway. In addition, with its fixed-wing capabilities and push prop in its aft, we can also have a more efficient forward flight than with just the VTOL. Every engineering project has a variety of risks that must be accounted for and prepared for. During our manufacturing phase of developments, all materials we use could have non-lethal to fatal effects should they not be used properly. For all sharp tools and machinery that were utilized, for instance the CNC hot wire cutter, drill presses, and more, we have a buddy system set up, which means if there is a tool that must be used, you must have a partner to ensure safety. In addition to this system, safety glasses, respirators, and gloves were always worn when any chemicals like epoxy, dangerous airborne materials like microballoons, or tooling was being used in the area that could affect the lungs or the eyes. During the mission, spilling propellers and electrical fires and shocks are some of the risks that can occur. To mitigate cuts from the propellers, all personnel must be at least 10 meters away when the aircraft is armed. To avoid electrical fires and shocks, no personnel are allowed to leave exposed wires anywhere in the lab or in the aircraft. And any flammable materials must not be utilized in areas of high electrical activity like the signals board and the power board. It is less likely, but catastrophic crashes that head towards members is also a risk. To mitigate this, pilots have been trained to fly waypoints not above the ground control station, which should be located 15 meters from the tarmac.
During our mission, the plane first goes through our pre-flight safety checklist, which includes physical inspection of motors, batteries, and aircraft structures, weather checks, and emergency procedures review. After passing the safety inspection, the aircraft takes off vertically using its 4 VTOL motors, climbs to 75 feet above ground level, before transitioning to autonomous forward flight. The plane then completes the mission objectives as described in the other sections. When the plane identifies the correct ground target, we release the payload from underneath the wing and it begins its guided descent onto the target. Because we've recently had issues getting our guided payload functionality fully working to the accuracy we desire, pictured in the video is an unguided airdrop. Once the mission is complete, the plane returns to the runway and enters a soft vertical descent using the VTOL motors. Once the aircraft has landed, the safety pilot disarms. We have successfully hit within the 20-foot threshold of airdrops in 4 out of 10 of our unguided airdrops, and we are still iterating on our guided payload algorithm. We hope to increase our accuracy performance in the weeks leading up to the competition. This competition season, Triton UAS has built an advanced, highly capable aircraft that accomplishes mission objectives with accuracy and safety. On the mechanical side, our VTOL quad plane design helps de-risk takeoff and landing. Using fundamental principles of good engineering, we have designed the plane to be extremely strong and lightweight, while still accomplishing all competition objectives. On the software side, our extensive software suite enables reliable mission autonomy while allowing for manual intervention and indentation if needed. We would like to thank the aircraft development team, the University of California, San Diego, as well as the entire SUAS competition staff for providing this incredible opportunity. Thank you.